All right, welcome, ladies and gentlemen, to lesson 2 for unit 6. We're going to look more at areas under a curve, and this time we're going to get outside of the LRAM, RRAM. We're going to look at what's called a definite integral. I've kind of briefly talked about it, but I never gave it a name just yet. So I'm going to define a couple things first. First thing is kind of what we did in the previous lesson. We looked at the areas of a whole bunch of rectangles, and that actually gets the name Riemann sums, named after a famous mathematician with the last name of Riemann. And it's basically, Riemann sums is basically the process of making infinitely many rectangles to estimate the area under a curve. Now, in the LRAM, RRAM, and MRAM, those rectangles have the same width, but sometimes you could actually, if you varied the width, you could actually find a little bit better area. And that's just the Riemann sums is just the process of making infinitely many rectangles. And in this particular case, this is really what the ugly, well, most of you are going to call this ugly. It's really just using sigma notation. It's the sum of all of the y values times all of the delta x's. And we talked about this in the previous lesson, saying that the y values, f of x, is the height of all of my rectangles times the change in width of all of my rectangles. So if I was to look at this kind of graphically here, some c value here, c sub k, we could have other c sub k or whatever, k2. The delta x here, this is delta x. We could find the area of some rectangle here, the height of which would be f of c sub k if we were to make our triangle or our shape like this. All right, so this is the height times the base, and it's really just the sum of all of those rectangular areas. And that's what we were dealing with previously. So let's go ahead and start this idea of integration. So all continuous functions are integrable. That means you can find the integral, by the way. Just like we have the word differentiable, means you can find the derivative. So this means if a function f is continuous on an interval, then its definite integral over ab exists. So this, first of all, is just an existence. And the definite integral is just, if you think about it, area. It's area underneath a curve. Now the big thing. This right here in the middle is our big new idea. This is the integral statement, okay? This big curved line here is the integral sign. The a and the b says we're going to integrate, or actually we're going to find the area. Let's look at this graphically. Let's look at this graphically here. We have some function, f of x, and we're integrating from a to b, and we're finding the area under this curve. So this is the integral of f from a to b. And this area is going to equal a number. So as soon as you find that number, you have evaluated the integral. Now we're going to learn how to do this using antiderivatives later. But right now we're looking at very basic functions to really sink in what this statement means. Here you'll understand that the function, the f of x, is what we call our integrand, and the dx represents the variable that we are doing integration with, just like we did dx tells me to take the derivative with respect to x. This tells me to take the integral with respect to x. Okay. Oops. Let me clear the screen here. What I want us to notice is that statement from before about the Riemann sums. As we get infinitely many rectangles and delta x gets closer and closer to 0, the limit of that sum is this integral statement. All right, area under a curve. If y is f of x is a non-negative and integrable over the closed interval a to b, then the area under the curve is given as this statement. So let me reiterate what we're talking about here. If we're talking about a function between a and b who is non-negative, between a and b, this function is always positive, so the area can be found as just doing the integral of the function from a to b. If your function is not positive, where it goes down here like this, from a to b, we can still find that area. It's just the opposite of if we were to just do it normally. Because really, if you think about it, this height is a y value that's negative. And the base of the rectangle here is positive, which means you get a negative area. But we say, since it's an area, we want to say it's negative, so we find the opposite of that value. This comes in very handy more and more as we get more and more deep into the area under the curve. So here's what else we can say. If you have a function that has both positive and negative values, so meaning if you have some function that looks like this between a and b, and you're trying to find the area between the curve or below the curve, we really mean find the area between the curve and the x-axis. So up here, this area is going to be positive, and down here, this area is going to be negative. So what we do is we split the area up. We split the integral up. It's the area above the x-axis minus the area below. And if you notice, if you subtract a negative area, you will get positive. So essentially, if this is a c value, what we're doing is we're integrating from c to b, which is a positive value, c to b in this particular case, because in my particular problem, this is the area above, minus the area from a to c of f of x dx. And we'll learn more rules like this, saying we can split up an integral any way we see fit. In this case, this helps me find the area below the curve, or below the x-axis, and the area above the x-axis, separate. I'm going to give us one little theorem here before we look at a couple of examples. The first one is if you have a constant function on the interval from a to b, if you really think about it, a constant function looks like this, where this is y equals c, or f of x equals c, and I tried to find the integral from a to b. You will understand that this is a rectangle, and the area of that rectangle, the height here is c, and the base of that rectangle is b minus a. So if I was to set this up saying, okay, we have a constant function, integral from a to b, we can say it's the integral from a to b of the constant function c, which is just a constant, it's a number, any number here, is going to equal c times the difference of b and a. What helps this here is the fact that we don't need to draw the graph, but I'm going to use the graph to help explain the y. All right, so if you have the integral of -7 to 4 of 5 dx, we know this is a constant value, so it's 5 times the difference of 4 minus -7. In this case, that's 11, so the area is 55. So the area under the curve is 55 units squared, or whatever we're dealing with in this particular case. All right, so using the notation, just a couple examples. I don't have them typed in here, but we can write a couple here. Let's go ahead and think about the integral from 0 to 4 of the function 2x dx. Now, we don't really know exactly everything that needs to be done here using anti-differentiation and all that sort of stuff because we're just starting out. So what we do is we look at this graphically. And if I was to draw the line y equals 2x, or f of x equals 2x, and I want to integrate between 0 and 4 and find the area below that curve, what we're going to be looking at right now is just finding the area of this shape. Well, it just so happens this shape is a triangle, and triangles we know are half base times height. The base is 4 minus 0. It'd be helpful if I know what 4 minus 0 is. It's 4 times the height is the height of the function at f of 4, because that's where the function needs to stop. We're going to f of 4. We know f of 4, 4 times 2 is 8, so it's 8. If we do 8 times 4 is 32, divided by 2 is 16. So the answer to this statement is 16. All right, by the way, we just figured out an integral, and we only just learned how to do integrals. We could also do something like this. We could say, okay, let's find the area of, let's go from 2 to 5 of the same function. Now, some of this might look a little bit familiar from last year, depending on, or the last class, the pre-calculus class, depends on how much you remember. So looking at the function 2x, it still does this, but now we only want to go from 2 to 5. Well, if I tried to find the area under this particular curve, this shape now looks a little bit more complex, but if you flip it over on the side, we get a trapezoid. And a trapezoid has area equal to 1/2 times the height times base 1 plus base 2. So the question is, what is what? Is height the height of this trapezoid? Well, the height in this case is the distance here. This is h, because we're looking at it on its side. So h in this case is 3, the difference between 5 and 2. And b1 and b2, this is f of 2 and f of 5. F of 2 is 4, and f of 5 is 10. 4 and 10 make 14. Half of that is 7 times 3 is 21. So the answer to this question here is 21. So notice I've used a couple area formulas that we need to remember how to do. This is for a trapezoid. We did the triangle. Another shape you might need to remember is the circle. If I was to integrate between, let's try -2 to 2 of the square root of 4 minus x squared dx. Most of us are going to look at this and go, I have no idea what's going on. Only because we forget what this equation is. If we look at this, y equals the square root of 4 minus x squared. If we were to square both sides, we get, we'd get y squared is equal to 4 minus x squared, which we'd get y squared plus, plus x squared is equal to 4. That is the equation to a circle. So this is the non-function version, but this is the function version. So technically what I have, from negative 2 to 2, I have negative 2 to 2, I have a circle, or actually half a circle, for the positive quadratic. And I'm trying to find the area below that curve. So we know area is equal to pi r squared. The problem is we don't have a full circle going on, so it's half of that value. So my r is 2. So my answer is 2 pi. All right, so the answer to this question is 2 pi. What else might we need to know here? Oh, let's try one that goes like this. Let's go from negative 4 to 2 of, let's go ahead and just use that 2x function again. So we're going from negative 4 to 2, which means I have to deal with some negative area. So if I was to split this up to think about only getting a positive answer, I want to find the area between the positive area. The positive area here is going to be 0 to 2 of 2x dx minus the negative area from negative 4 to 0 of 2x dx. So the area here, this distance is 2. The height is f of 2. So it's 1/2 times 2 times f of 2, which is 4, minus, now remember that this is a negative area here, technically. So it's 1/2 times negative 4, because that's the width this direction. It's negative 4 if you think about it this way. Actually, let's think of it as a 4. And this is f of negative 4. F of negative 4 is negative 8. We do our problem here. We get 8 divided by 2, which is 4, minus a negative 16. So it's plus 16, and the area is 20. All right, one last thing I'm going to leave you with. It's not even a problem. It's just a statement. If you recall from last year, and one of the problems that they give in the notes section is this is the sine function, sine of x, going from pi to 2 pi, or from 0 to 2 pi. The area right here under one curve is equal to 2. Make a note of that because that's very helpful, because we don't know how to integrate sine of x yet, but we can use what we know about graphs and the area under one curve equaling 2. All right, I'm going to leave you guys with that. Here's your assignment. Again, I haven't quite finished our assignment sheet yet, but I will hopefully get it to you guys tomorrow, if not later than that. But here is the assignment for lesson 2. I hope you guys learned a few things, and I will see you guys tomorrow.